The sievert is a derived unit of ionizing radiation dose in the International System of Units. It is a measure of the health effect of low levels of ionizing radiation on the human body. Quantities that are measured in sieverts are intended to represent the stochastic health risk, which for radiation dose assessment is defined as the probability of cancer induction and genetic damage. The sievert is used for radiation dose quantities such as equivalent dose, effective dose, and committed dose. It is used both to represent the risk of the effect of external radiation from sources outside the body, and the effect of internal irradiation due to inhaled or ingested radioactive substances. Conventionally, the sievert is not used for high levels of radiation which produce deterministic effects, which is the severity of acute tissue damage which is certain to happen. These effects are compared to the physical quantity absorbed dose measured by unit Gray. To enable consideration of stochastic health risk, calculations are performed to convert the physical quantity absorbed dose into equivalent and effective doses, the details of which depend on the radiation type and biological context. For applications in radiation protection and dosimetry assessment, the International Commission on Radiological Protection and International Commission on Radiation Units and Measurements have published recommendations and data which are used to calculate these. The sievert is of fundamental importance in dosimetry and radiation protection, and is named after Rolf Maximilian Sievert, a Swedish medical physicist renowned for work on radiation dosage measurement and research into the biological effects of radiation. One sievert carries with it a 5.5% chance of eventually developing cancer. Doses greater than 1 sievert received over a short time period are likely to cause radiation poisoning, possibly leading to death within weeks. 1 sievert equals 100 rem. The rem is an older, non-SI unit of measurement. To enable a comprehensive view of the sievert, this article deals with the definition of the sievert as an SI unit, summarizes the recommendations of the ICAU and Icrp on how the sievert is calculated, includes a guide to the effects of ionizing radiation as measured in sieverts, and gives examples of approximate figures of dose uptake in certain situations. Definition: CIPM definition of the sievert. The SI definition given by the International Committee for Weights and Measures says, the quantity dose equivalent H is the product of the absorbed dose D of ionizing radiation and the dimensionless factor of Q defined as a function of linear energy transferred by the ICAU, H equals Q D. The value of Q is not defined further by CIPM, but it requires the use of the relevant ICAU and Icrp recommendations to provide this value. The CIPM also says that in order to avoid any risk of confusion between the absorbed dose D and the dose equivalent H, the special names for the respective units should be used, that is, the name Gray should be used instead of joules per kilogram for the unit of absorbed dose D and the name Sievert instead of joules per kilogram for the unit of dose equivalent H. In summary, the Gray quantity D, 1 Gray equals 1 joule per kilogram, a physical quantity. 1 Gray is the deposit of a joule of radiation energy in a kilogram of matter or tissue. The sievert, quantity H, 1 sievert equals 1 joule per kilogram, a biological effect. The sievert represents the equivalent biological effect of the deposit of a joule of radiation energy in a kilogram of human tissue. The equivalence to absorbed dose is denoted by Q. Icrp definition of the sievert. The Icrp definition of the sievert is: the sievert is the special name for the SI unit of equivalent dose, effective dose, and operational dose quantities. The unit is joule per kilogram. The sievert is used for a number of dose quantities which are described in this article and are part of the International Radiological Protection System devised and defined by the Icrp and ICAU. Naming conventions: these dose quantities have specific purposes and meanings, but there can be confusion between, for instance, equivalent dose and dose equivalent. Although the CIPM definition states that the linear energy transfer function of the ICAU is used in calculating the biological effect, the Icrp in 1990 developed the protection dose quantities effective and equivalent dose, which are calculated from more complex computational models and are distinguished by not having the words dose equivalent in their name. Only the operational dose quantities which use Q for calculation retain these words. In the US there are further differently named dose quantities which are not part of the Icrp system of quantities. External dose quantities. The Civet is used to represent the biological effects of different forms of external ionizing radiation on various types of human tissue. Some quantities cannot be practically measured, but they must be related to actual instrumentation and dosimetry measurements. The resultant complexity has required the creation of a number of different dose quantities within a coherent system developed by the ICRU working with the Icrp. The external dose quantities and their relationships are shown in the accompanying diagram. Physical quantities. These are directly measurable physical quantities in which no allowance has been made for biological effects. Radiation fluence is the number of radiation particles impinging per unit area per unit time. Kerma is the ionizing effect of the radiation field, and absorbed dose is the amount of radiation energy deposited per unit mass. Protection quantities. The protection quantities are used as limiting quantities to specify exposure limits to ensure, in the words of Icrp, that the occurrence of stochastic health effects is kept below unacceptable levels and that tissue reactions are avoided. However, these quantities cannot be practically measured and are a calculated value of dose of organs of the human body, which is arrived at by using anthropomorphic phantoms. These are 3D computational models of the human body which take into account a number of complex effects such as body self-shielding and internal scattering of radiation. As protection quantities cannot practically be measured, operational quantities are used to relate them to practical radiation instrument and dosimeter responses. Operational quantities are aimed at providing an estimate or upper limit for the value of the protection quantities related to an exposure. They are often used in practical regulations or guidance. These relate real-life operational instrument measurements and responses to the calculated protection quantities. Simple phantoms relate operational quantities to measured irradiation. According to the Icrp, the ICRU sphere phantom in most cases adequately approximates the human body as regards the scattering and attenuation of the radiation fields under consideration. The slab phantom is used to represent the human torso for calibration of whole-body dosimeters. Instrument and dosimetry response. This is an actual reading obtained from such as an ambient dose gamma monitor, or a personal dosimeter. Calculating protection dose quantities. The Civet is used in external radiation protection when discussing equivalent dose, and effective dose. These dose quantities are weighted averages of absorbed dose designed to be representative of the stochastic health effects of radiation, and use of the Civet implies that appropriate weighting factors have been applied to the absorbed dose measurement or calculation. The Icrp calculation provides two weighting factors to enable the calculation of protection quantities. A1. The radiation factor WR, which is specific for radiation type R. This is used in calculating the equivalent dose HT, which can be for the whole body or for individual organs. A2. The tissue weighting factor WT, which is specific for tissue type T being irradiated. This is used with WR to calculate the contributory organ doses to arrive at an effective dose E for non-uniform irradiation. When a whole body is irradiated uniformly, only the radiation weighting factor WR is used, and the effective dose equals the whole body equivalent dose. But if the irradiation of a body is partial or non-uniform, the tissue factor WT is used to calculate dose to each organ or tissue. These are then summed to obtain the effective dose. In the case of uniform irradiation of the human body, these sum it to 1, but in the case of partial or non-uniform irradiation, they will sum it to a lower value depending on the organs concerned, reflecting the lower overall health effect. The calculation process is shown on the accompanying diagram. This approach calculates the biological risk contribution to the whole body, taking into account complete or partial irradiation, and the radiation type or types. The values of these weighting factors are conservatively chosen to be greater than the bulk of experimental values observed for the most sensitive cell types, based on averages of those obtained for the human population. Radiation type weighting factor WR. As various radiation types have different biological effects for the same deposited energy, a corrective radiation weighting factor WR, is applied to convert the physical unit of the gray into the equivalent dose due to the radiation type concerned. The equivalent dose is calculated by multiplying the absorbed energy, averaged by mass over an organ or tissue of interest, by a radiation weighting factor appropriate to the type and energy of radiation. To obtain the equivalent dose for a mix of radiation types and energies, a sum is taken over all types of radiation energy dose, where HT is the equivalent dose absorbed by tissue T, dt, R is the absorbed dose in tissue T by radiation type R, WR is the radiation weighting factor defined by regulation. Thus, for example, an absorbed dose of 1 gray by alpha particles will lead to an equivalent dose of 20 Civet. This may appear to lead to a paradox, as this would suggest that the energy of the incident radiation field in joules has increased by a factor of 20, thereby violating the laws of conservation of energy. However, this is not the case. The civet is used only to convey the fact that the biological effect of absorbing a gray of alpha particles would result in a 20-fold increase in the amount of biological effects that one would observe by absorbing a gray of X-rays. It is this biological component that is being expressed when using civets rather than the actual physical energy delivered by the incident absorbed radiation. Tissue type weighting factor WT. The second weighting factor is the tissue factor WT, but it is used only if there has been non-uniform irradiation of a body. If the body has been subject to uniform irradiation, the effective dose equals the whole body equivalent dose, and only the radiation weighting factor WR is used. But if there is partial or non-uniform body irradiation, the calculation must take account of the individual organ doses received, because the sensitivity of each organ to irradiation depends on their tissue type. This summed dose from only those organs concerned gives the effective dose for the whole body. The tissue weighting factor is used to calculate those individual organ dose contributions. The Icrp values for WT are given in the table shown here. The article on effective dose gives the method of calculation. The absorbed dose is first corrected for the radiation type to give the equivalent dose, and then corrected for the tissue receiving the radiation. Some tissues like bone marrow are particularly sensitive to radiation, so they are given a weighting factor that is disproportionately large relative to the fraction of body mass they represent. Other tissues like the hard bone surface are particularly insensitive to radiation and are assigned a disproportionately low weighting factor. In summary, the sum of tissue-weighted doses to each irradiated organ or tissue of the body adds up to the effective dose for the body. The use of effective dose enables comparisons of overall dose received regardless of the extent of body irradiation. Operational quantities. The operational quantities are used in practical applications for monitoring and investigating external exposure situations. They are defined for practical operational measurements and assessment of doses in the body. 3 external operational dose quantities were devised to relate operational dosimeter and instrument measurements to the calculated protection quantities. Also devised were 2 phantoms, the ICRU slab, and sphere phantoms, which relate these quantities to incident radiation quantities using the Q-L calculation. Ambient dose equivalent. This is used for area monitoring of penetrating radiation and is usually expressed as the quantity H10. This means the radiation is equivalent to that found 10 ohm within the ICRU sphere phantom in the direction of origin of the field. An example of penetrating radiation is gamma rays. Directional dose equivalent. This is used for area monitoring of low penetrating radiation and is usually expressed as the quantity H, 0.07. This means the radiation is equivalent to that found at a depth of 0.07 mm in the ICRU sphere phantom. An example of low penetrating radiation is alpha particles. In radiological protection practice, value of omega is usually not specified as the dose is usually at a maximum at the point of interest. Personal dose equivalent. This is used for individual dose monitoring, such as with a personal dosimeter worn on the body. The recommended depth for assessment is 10 ohm, which gives the quantity HP, 10. Internal dose quantities. The civet is used for human internal dose quantities in calculating committed dose. This is dose from radionuclides which have been ingested or inhaled into the human body, and thereby committed to irradiate the body for a period of time. The concepts of calculating protection quantities as described for external radiation applies, but as the source of radiation is within the tissue of the body, the calculation of absorbed organ dose uses different coefficients and irradiation mechanisms. The Icrp defines committed effective dose, ET, as the sum of the products of the committed organ or tissue equivalent doses and the appropriate tissue weighting factors WT, where T is the integration time in years following the intake. The commitment period is taken to be 50 years for adults, and to age 70 years for children. The Icrp further states for internal exposure, committed effective doses are generally determined from an assessment of the intakes of radionuclides from bioassay measurements or other quantities. The radiation dose is determined from the intake using recommended dose coefficients. A committed dose from an internal source is intended to carry the same effective risk as the same amount of equivalent dose applied uniformly to the whole body from an external source, or the same amount of effective dose applied to part of the body. Health effects. Ionizing radiation has deterministic and stochastic effects on human health. Deterministic events happen with certainty, with the resulting health conditions occurring in every individual who received the same high dose. Stochastic events are inherently random, with most individuals in a group failing to ever exhibit any causal negative health effects after exposure, while an indeterministic random minority do, often with the resulting subtle negative health effects being observable only after large detailed epidemiology studies. The use of the Civet implies that only stochastic effects are being considered, and to avoid confusion deterministic effects are conventionally compared to values of absorbed dose expressed by the SI unit Gray. Stochastic effects are those that occur randomly, such as radiation-induced cancer. The consensus of nuclear regulators, the nuclear industry, governments, some Academy of Sciences and the UNSCEAR, is that the incidence of cancers due to ionizing radiation can be modeled as increasing linearly with effective dose at a rate of 5.5% per sievert. Individual studies, alternative models, and earlier versions of the industry consensus have produced other risk estimates scattered around this consensus model. There is general agreement that the risk is much higher for infants and fetuses than adults, higher for the middle-aged than for seniors, and higher for women than for men, though there is no quantitative consensus about this. Deterministic effects. The deterministic effects that can lead to acute radiation syndrome only occur in the case of high doses and high dose rates and are conventionally not measured using the unit Civet. A model of deterministic risk would require different weighting factors than are used in the calculation of equivalent and effective dose. The United Nations Scientific Committee on the Effects of Atomic Radiation report of 2012 states that no discernible acute tissue effects of exposures below 0.1 sievert appear to exist, which is compatible with known cellular repair mechanisms. Icrp dose limits. The International Commission on Radiological Protection recommends limiting artificial irradiation. For occupational exposure, the limit is 50 msv in a single year with a maximum of 100 msv in a consecutive 5-year period, and for the public to an average of 1 msv of effective dose per year, not including medical and occupational exposures. For comparison, radiation levels inside the U.S. Capitol building are such that a human body would receive an additional dose rate of 0.85 msv, close to the regulatory limit, because of the uranium content of the granite structure. According to the conservative Icrp model, someone who spent 20 years inside the Capitol building would have an extra 1 in 1,000 chance of getting cancer, over and above any other existing risk. That existing risk is much higher. An average American would have a 10% chance of getting cancer during this same 20-year period, even without any exposure to artificial radiation. See Natural Epidemiology of Cancer and Cancer Rates. These estimates are, however, unmindful of every living cell's natural repair mechanisms, evolved over a few billion years of exposure to environmental chemical and radiation threats that were higher in the past and exaggerated by the evolution of oxygen metabolism, a challenging trade-off made by life. Dose examples. Significant radiation doses are not frequently encountered in everyday life. The following examples can help illustrate relative magnitudes. These are meant to be examples only, not a comprehensive list of possible radiation doses. An acute dose is one that occurs over a short and finite period of time, while a chronic dose is a dose that continues for an extended period of time so that it is better described by a dose rate. Dose examples, dose rate examples. All conversions between hours and years have assumed continuous presence in a steady field, disregarding known fluctuations, intermittent exposure and radioactive decay. Converted values are shown in parentheses. Notes on examples. History. The Civet has its origin in the Röntgen equivalent man, which was derived from CGS units. The International Commission on Radiation Units and Measurements promoted a switch to coherent SI units in the 1970s, and announced in 1976 that it planned to formulate a suitable unit for equivalent dose. The Icrp preempted the ICAU by introducing the Civet in 1977. The Civet was adopted by the International Committee for Weights and Measures in 1980, 5 years after adopting the Gray. The CIPM then issued an explanation in 1984, recommending when the Civet should be used as opposed to the Gray. That explanation was updated in 2002 to bring it closer to the Icrp's definition of equivalent dose, which had changed in 1990. Specifically, the Icrp had renamed the dose equivalent to equivalent dose, renamed the quality factor to radiation weighting factor, and dropped another weighting factor N in 1990. In 2002, the CIPM similarly dropped the weighting factor N from their explanation but otherwise kept the old terminology and symbols. This explanation only appears in the appendix to the SI brochure and is not part of the definition of the Civet. Common SI usage. This SI unit is named after Rolf Maximilian Sievert. As with every international system of units whose name is derived from the proper name of a person, the first letter of its symbol is uppercase. However, when an SI unit is spelled out in English, it should always begin with a lowercase letter, except in a situation where any word in that position would be capitalized, such as at the beginning of a sentence or in capitalized material such as a title. Note that degree Celsius conforms to this rule because the D is lowercase a euro are based on the International System of Units, section 5.2. Frequently used SI prefixes are the millisievert and microsievert, and commonly used units for time derivative or dose rate indications on instruments and warnings for radiological protection are I1/4 sievert per hour and MSVH. Regulatory limits in chronic doses are often given in units of MSVA or sievert per hour, where they are understood to represent an average over the entire year. In many occupational scenarios, the hourly dose rate might fluctuate to levels thousands of times higher for a brief period of time, without infringing on the annual limits. The conversion from hours to years varies because of leap years and exposure schedules, but approximate conversions are, 1 MSVH equals 8.766 a sievert per hour, 114.1 AI1/4 sievert per hour equals 1 a sievert per hour. Conversion from hourly rates to annual rates is further complicated by seasonal fluctuations in natural radiation, decay of artificial sources, and intermittent proximity between humans and sources. The Icrp once adopted fixed conversion for occupational exposure, although these have not appeared in recent documents. 8 AH equals 1 a day, 40 AH equals 1 a week, 50 a weeks equals 1 a year. Therefore, for occupation exposures of that time period, 1 MSVH equals 2 a sievert per hour, 500 AA micron sievert per hour equals 1 a sievert per hour. Radiation-related quantities. The following table shows radiation quantities in SI and non-SI units. Although the United States Nuclear Regulatory Commission permits the use of the units Curie, Rad, and Rem alongside SI units, the European Units of Measurement directives required that their use for public health purposes be phased out by December 31, 1985. Rem equivalents. An older unit for the dose equivalent is the Rem, still often used in the United States. 1 sievert is equal to 100 Rem. See also, background radiation, becquerel, Computational human phantom, a means of modeling radiation protection quantities, counts per minute, fluence, linear energy transfer, orders of magnitude. Example exposure scenarios, radiation poisoning, relative biological effectiveness, Rutherford, Sverdrup, notes. References: Report of the United Nations Scientific Committee on the Effects of Atomic Radiation to the General Assembly, United Nations Scientific Community on the Effects of Atomic Radiation, external links, Glover, Paul. Miller, Sieverts and Radiation. 60 Symbols. Brady Heron for the University of Nottingham. 2, The Confusing World of Radiation Dosimetry. M. A. Boyd, U.S. Environmental Protection Agency 2009. An account of chronological differences between U.S. and Icrp dosimetry systems. Iridos, the European Radiation Dosimetry Group.